Hi guys, welcome to Algorithms Made Easy. My name is Khushbu and in this video we are going to see the question merge two binary trees. You are given two binary tree, root 1 and root 2. Imagine that when you put one of them to cover the other, some nodes of the two trees are overlapped while the others are not. You need to merge the two trees in a new binary tree. The merge rule is that if two nodes overlap, then sum the node values up as the new value of the merged node. Otherwise, the non-null node will be used as the node of the new tree. After we are doing this, we need to return the merged tree. The merging process must start from the root of both the trees. This is the node that is given to us, and now let's go to example number 1. So, these are the two trees that are given to us in the example number 1. And over here we see that the structure of both the trees is different. So what will happen when we merge these two trees? If we try to perform an overlap of these, we see that the three nodes are overlapping while these three are not overlapping. So according to the rule, we need to add the values for the overlapping nodes, and otherwise we need to add the nodes that are there in the tree to form a resultant merged tree. So this becomes our resultant merged tree, wherein we have the three overlapped nodes, one node from the first tree and these two nodes are from the second tree. I hope the example is clear to you. Now let's go and understand the different approaches that we could apply in order to solve this question. The first one is a recursion method, wherein we are going to use basic recursive tree traversal in order to traverse over the tree and find the merged tree. The another way would be an iterative way to do so by using either a pre-order, in-order or post-order. The third one is BFS, which is iterative, which means the level order traversal of the tree. We'll see each one of these and we'll also see the questions that can come up in an interview while you implement one of these approaches. So let's start with the first one. Now before starting with that, we need to first jot down all the conditions that can occur while merging the tree. So these are the 4 conditions that we can have. The first one is that the node in both the trees is null. In that case, we do not need to do anything because the resultant tree node will also be null. The second case is that the node in the first tree is null, wherein we have the node in the second tree. So in that case, we will be considering the node from tree 2. Similar case can appear with tree 1 also. That is, we have a node in tree 1, but the same node in tree 2 is null. So in that case, we will just consider the node that is present in the first tree. And the last condition is the overlap condition, wherein we have the nodes in both the trees and so we need to do the sum of both the nodes. So these are the basic 4 conditions that we are going to use in all the 3 approaches, but only the traversal is going to change. So let's go through the first one, which is recursive DFS. In this we are going to use pre-order traversal and we are going to use the same example. So let's take these two trees and perform a merge on this. So according to the pre-order traversal, we are going to take the root, process it, then recursively process the left tree and then recursively process the right tree. This is the basic pre-order traversal that we have already seen in our trees chapter. But let's go through it step by step over here. Now, while we see the root nodes, both of these are not null, and so this is the overlap condition and we need to consider the sum of the values of both these nodes. So let's alter the tree 1, that is the tree which is in the blue color, and we'll output that tree as our merged tree. So we'll change its value 2 plus 1, which gives us 3. Now once we have this processed, we are going to process the left subtree and the right subtree recursively. And so we go to its left and again we have an overlap, and so we'll add the values and the resultant will be 4 and we'll go to its left. Now over here, as you can see, we have the node in the first tree but we do not have the left node in the second tree, and so we just need to consider the non-null node, which is 5, and we keep it as is. Now we need to go to the right of this root node 4 because our left subtree has been processed for this. So over here you can see that the first tree does not have a right node, but the second tree has it. So we need to attach this node to its right, and so it goes over here. Now as we have processed the left tree, we go to the right and process these nodes. Again, if you see over here we have a overlap, and so we do addition of both the nodes, which gives us 5, and we go to its left. Now as we go to its left, we see that the left of both these trees for this particular node is null, and so we do not need to consider anything, or we do not need to update anything, and we can move forward and go to its right. For this right node, tree 1's right is null, so we are going to consider the right for tree 2 node, and so that gives us 7. And now our entire tree is merged, and this becomes our resultant tree. So the solution here is very simple. That is, we are going to follow pre-ordered reversal, and we are going to follow the conditions to check whether we can sum up the node values or we need to take the nodes from either of the trees. So let's first write the code for this, and then we'll see the other approaches as well. Okay. So we have a few conditions. That is, if T1 is null, we need to consider T2. Similarly, if T2 is null, we consider T1. Otherwise, we do sum of T1 and T2. Now, all this is going to happen with pre-order traversal, which means we are going to first process the root, then go to its left, and then go to its right. So let's go ahead and write some code for it. So let's take the condition 1, which is if T1 is null, give out T2, vice versa. If T2 is null, return T1, and if nothing of this is there, then we update T1 with sum of T1 and T2, and we recursively process the left tree and the right tree. So T1.left equals merge trees T1.left, T2.left, and similarly with right. Finally, our answer is going to be the tree T1. So we just need to return it. And that's it. Let's run this code. Okay, so let's just change it to T1 and T2 and run this code. So it's giving a perfect result. Let's submit this. And it got submitted. The time complexity for this solution is going to be O of n because we have to iterate over all the nodes, and the space complexity is going to be O of h, that is the height of the tree, to store the recursion stack. Now, this O of h can become O of n if the tree is skewed tree. Now, one of the questions that an interviewer can ask is, tell me the drawbacks or tell me the cases where the solution will fail. Think upon it, and we'll go back to our next solution with the answer. Okay, the answer to that question is that particular solution can go and run into Stack Overflow, because for maintaining the recursion stack, the program is going to use your memory, which is the heap memory. Now, how can you avoid it? You can use an iterative solution to avoid it. Now, there is one more question that the interviewer will ask you if you give the solution as use the iterative approach instead of a recursive one. We'll see the answer to it after we are done with this particular approach. So stay tuned and let's move ahead. The answer to the question is that we can use the iterative method to get away with the Stack Overflow issue. Now, how does this help and when will this fail? That we'll see after we have covered this method. So stay tuned and let's go ahead. In this also we are going to use the same example, and let's start with it. Iterative traversal requires a stack or a queue. depending on what kind of traversal we are going to perform. Since it is DFS, we are going to use stack. If it was a level order traversal, we would have used queue. If you are not aware of the traversal methods, you can check out our tree playlist wherein we have all the traversal methods explained in detail with the examples. Now, in here we are going to first add our root nodes into the stack. We are going to add both the nodes as we are going to process both the trees at the same time. So, the stack can contain either a pair of tree node or you can have an array of tree node. Now, once we have these tree node into the stack, now what we are going to do is we are going to start popping out from the stack and processing the nodes while the stack is having some elements in it. So, we are going to pop this node out and process it. For processing, we need to check our conditions. Now, since we have the non-null nodes over here, this is an overlap and so we need to sum it up. And the sum will go into the first tree because we are going to modify the first tree itself. So, this node over here will become 3 and then we are going to process its left and right. So, we'll add those node pairs into the stack. Now, this gives us left pair which is 3 and 1 and the right pair 2 and 3 into the stack. Now, we'll go and pop one of them out and process it. So, this will give us the right node out, and for processing it, we are going to add the values which will give me 5. Now, while processing its left and right, we can see that both these nodes, that is these two nodes, are not having the left node and so we do not need to process it. For the right one, only one of them has a right node. So, we do not need to do anything but just add this non-null node into our resulting tree, which gives me 7 over here. So, now the processing of this node completes. So, we now pop the other one out and process them. Over here also we have 2 non-null nodes. We add it, which gives us 4, and now we are going to process its left and right. Similarly, for this node, we have left for one of the tree and right for the another tree. So, we are only going to consider the non-null node. And so, we keep 5 as it is and we add 4 from this tree into our resultant tree, which gives us our output. Now, how do we say that we need to stop? The stack has now become empty and so we can stop our processing and return the first tree that we have updated to form the merged tree. So, this was the iterative DFS. Now, if you would see, the time complexity for any of the approaches over here is going to remain same, which is O of n, because you need to go to each and every node in order to merge the trees. The space complexity for the first one was O of h, which was going to be stored in the heap memory. The space complexity for this approach is also going to be O of h because we are mimicking the recursion stack, but we are mimicking it in our own user defined stack. So, this is not going to go into our heap memory and so we won't get the stack overflow issue, but we can get an out of memory issue over here if the tree becomes skewed, because in case of a skewed tree, the space complexity will go up to O of n, that is the number of nodes that are present into a tree. So, the stack overflow issue can be overcome by using iterative. And now, the second one more question that the interviewer can ask in this particular approach is that is there a way you can increase the memory? So, the answer for that is yes. You can configure the memory that you can allocate to the stack that is going to be used by your JVMs for your programs. And so, this issue can be resolved or it can be leveraged. Now that we know the answer to the question and also the explanation for the iterative DFS, let's go and code it out. So, in this also we are going to update our first tree. The first two conditions remain the same while we are going to take a stack over here. So let's take, and in the stack you are going to add or push the roots T1 and T2. Once we have the basic initial stack ready, we are going to loop while stack is not empty. So let's take that condition, and inside this we are going to check for our cases. Before that, we are going to just pop out the element from the stack. So pop the element, and in the stack we'll never encounter any value wherein any of the two nodes is null. So what we are going to do over here is process the node. So for processing this, we need to add the value for the 0th and first element of this array. So we take this and we are going to update the first tree. Now we are going to take our conditions wherein current of 0 is null, current of 1 is not null. Second case could be vice versa, and third is both not null. So in this case we are going to take the non-null element, and here we are going to add it in stack for the further process. So we need to do this for both left and the right tree. So let's go to the left tree first. So here we are going to take the condition, that is my current of 0 dot left, if that is equal to null, I am going to do current of 0 dot left equal to current of 1 dot left. Otherwise, if current of 0 is not null and also the current of 1 is not null, then we are going to add it into the stack. So stack dot push new tree node current of 0 dot left comma current of 1 dot left. Same thing we need to do with the right tree as well. So let's copy this, and instead of left we'll just make it right. So this will process the left tree as well as the right tree, and the while loop will take care of processing the root node. Finally, we return the tree T1, and that's all. Let's run this code, and we have a issue. We need to put a square bracket, and we are getting a perfect result. Let's submit this, and it got submitted. The time complexity for this particular solution is going to be O of n, as we are still going to go over all the nodes that are there. The space complexity will also be O of h, because we are going to have a stack that can accommodate at most O of h nodes at a particular time. But here also there is a catch. Now what happens if you are only going to get skew trees as your example? In that case, your space complexity is always going to be O of n, if and only if the trees are skewed. So if the trees are going to be skewed, this can be made efficient by using level order traversal, because in level order traversal you are going to go level wise, and at most number of nodes that you will be storing would be of 2 levels. So let's go and see that solution. That is not the perfect solution for your perfect binary tree, but it is going to help you in case wherein you have a skewed tree. Level order traversal is nothing but BFS, and this is also an iterative method. So we take the same example, and in this we are going to take a queue. Now level order traversal is also a topic that we have already covered in our tree section, so you can go and check out that videos for a in-depth explanation. Over here we are going to go through the process. So we are going to take a queue, and as an initial step we add the root nodes. Similarly, as we have done in our stack approach, we are going to use an array of tree node or a pair of tree node to store into our queue. Now once we have the root added, this becomes the size of our current level. So I have shown this current level with this particular line. Now what we do after this? After this we are again going to pop these elements out or remove from the queue, which will give us these two nodes, and we are going to process these and add its left and right into the queue. So again, while processing, sum this up because we are going to merge these nodes and add the left and right into the queue. Now once we have added the left and right, now these are going to become the end of the current level, and so this is marked by this particular line. Next we are going to pop this out, process it by merging the nodes. So we are going to add the numbers, which gives us 4, and after processing this we are going to go to its left and right. So as we know, over here the left is present for this tree, the right is present for this tree. So we are going to just process these nodes and we are not going to add it in our queue as we did it for stack also. So 5 remains here, 4 gets appended to this, and we have processed this particular node. Next we pop out the another node and do the same. So for this node also we are going to add the values up, and then we are going to process left and right. Since both the lefts are not there, it will be null. For the rights, we have a right in this particular tree, so that gets appended into our merge tree. So the condition is that if the left or right for tree 2 node, that is this second tree, is null, we are not going to require any processing because we can keep the same left tree as is. But if for tree 1 we are not having the node, we need to take the node from tree 2. So we take it, and that's done because the queue has now become empty, and this becomes our result. So that's it with the explanation. For a detailed explanation on level order traversal, I'll ask you guys to go and check out the trees chapter, wherein you will find a detailed explanation of what we are doing and why we are doing it. For this question, now let's go and code this particular approach out. The first two conditions are going to remain the same. Over here, instead of stack, we are going to use a queue. So let's use a queue, and this is going to be a linked list. Instead of st, we are going to do queue. So we are going to push this tree node, and while my queue is not empty, I am going to remove one of the node. Now, as we said, if the right tree is empty, we do not need to do anything. So if my current of 1 is not equal to null, then we are going to process, and so we are going to use the same thing. Current of 0.val is going to get updated, and we are going to have the conditions for left and right. So let's take it over here, and then we'll change it as we need it. So now over here we are always going to have this as not null. So there is no case this that is going to appear. So let's remove this out, and now if current is null, I need to just consider current of 1. That was the mistake in the earlier approach as well. In the comments, and if this is not null, that is if current of 0 is not null, we are going to add it into our queue, and that's it. Same thing we are going to do for the right and left. So if this is equal to null, we are going to take this and else. So we do not need this if condition. We are going to do queue dot add, and same with right one. So we are just having a if condition to check my left, that is the first tree, is not empty, and that's all. Let's run this code, and we have used a push somewhere. Let's change it to add, that is the queue convention, and let's run it again. This becomes queue. Let's see if we have used it somewhere else. and not. Let's run this. And we are getting a perfect result. Let's submit this. And it got submitted. The time complexity as set remains the same, which is O of n. The space complexity would be the maximum number of nodes that can be in any of the two levels. So it goes to 2 raised to h plus 2 raised to h minus 1, which will give you a time complexity of 2 raised to h. So this is obviously more than the time complexity for the DFS approaches, but this will perform well space-wise, wherein you are only going to have a skew tree. So that's it for this question, guys. I hope you like the video, and I'll see you in another one. So till then, keep learning, keep coding. Bye-bye.